Hello everyone, I welcome you all to this channel Catalytic Guru. In the very first video, we are going to look into the ideal reactors. Ideal, the term means on papers, or we expect certain things to behave in a certain way. Right? An ideal child is someone who respects and responds well to his parents. So similarly, ideal reactors are those reactors where we expect them to behave in a certain way. We want the reactor to behave, although in reality that doesn't happen. We expect the reactors to behave in a certain way, and there are two extremes possible, and those are well-known mixed flow reactor and the plug flow reactor. Right. So when we talk of these reactors, we have to, when I even try to explain what this means, you have to keep in mind that these are just fantasies. Neither a mixed flow reactor nor a plug flow reactor does exist in reality. It can never exist. So we are going to talk of fantasy. So when we talk of fantasy, you need a lot of imagination. Now we'll start with the mixed flow reactor. I will try to draw it as beautifully as possible, as nice as possible. So there is nothing but a tank, and this tank is provided with a stirrer. Right. So this is a mixed flow reactor in a very vague sense, where you have something getting in and something leaving the reactor, and whatever is present in the reactor is extremely well mixed. I use the term again, where mixing is perfect. So when they say mixing is perfect, which means at every point of this reactor, I take some random points, this. At every point of the reactor, the composition is same at a given time. So we know the reaction is happening inside the reactor, which means the composition is changing with respect to time, but not with respect to the space. So any point inside this particular reactor will have the same concentrations throughout at a given point of time. Now it can be beautifully compared with a very famous ideology, a political ideology, which is communism. You all know what communism is. Communism is an extreme political ideology in which everyone is given equal share and all those things. I don't want to get into the details, but when there is communism, which means ideal communism again, which doesn't exist in reality, just like the ideal mixed flow reactor, we have an equal share of concentration. There is an equality, right? There is an equality in a very vague sense. One second. Right? So you can take this analogy and you can proceed to the next stage, which is a plug flow reactor. A plug flow reactor is like this, a tubular reactor, something they call it as a tubular reactor, where, so it's straightforward, right? When I say mixing is perfect in case of a mixed flow reactor, then here there is no mixing. I use this term very carefully. I will say in the axial direction. I will come to what this actually means. I will come back to this, but just note that there is no mixing in the axial direction. So when you have a plug flow reactor, same way, the reactant enters and the product leaves this reactor. So you can expect a change. Right? If a reaction, say A to B, is happening, the concentration of A is high here and concentration of A is low here, thanks to the reaction. Right? So this difference, so again by the law of nature, if one extreme can be compared to the political ideology communism, obviously the other extreme can be compared to the political ideology capitalism. So capitalism, I will better explain it with a cartoon which I sourced from Google. You have this here. So this is a classic example of capitalism, although it kind of trolls capitalism. I have no intentions in trolling any of the ideologies. I just thought this is a very good picture to explain the plug flow reactor, nothing more than that. So I will parallelly draw a plug flow reactor here, side by side. Now just imagine this 90-degree this way, right? Just like it's horizontal and this is vertical. Now you can see in this picture there are various six. Like this is a working class and this is a ruling class, which means on a very general sense I will say this is high, not to hurt anyone's feelings, but this is low. Right. Similarly, in a plug flow reactor, when reactor enters inside, this area will be high in concentration of reactants, and this area will be low in concentration of reactants. And one more beautiful thing, if you observe in this, all the individual sects, for example, this are very well mixed, right? People of this particular class are extremely well mixed. People of this particular class are extremely well mixed. People of this particular class are extremely well mixed. Similarly, in a plug flow reactor, if you take, this is a plug flow reactor, in a given cross section, this is extremely well mixed in the radial direction, right? But if you compare it with the very next sect, this and this won't be matching. There will be differences, but within a particular sect there will be extremely good mixing. So you can consider ideally this every sect is a MFR, every sect is a mixed flow reactor. So a plug flow reactor like this, I'm drawing this very largely, but just assume that these are infinitely well divided, right? So in that case what happens, everything is a mixed flow reactor. That's why you would have heard the statement somewhere before, like I'll write the statement itself just to make you clear. Plug flow reactors, so I'm sorry about this, plug flow reactors can be taken as infinite MFR in series. So when there are large number of MFRs in series, they will tend to behave like a PFR. So at least say there are only 2 MFRs, they will behave like a PFR. Okay? So I hope this analogy was clear. Similarly, every single thing, if I had a cartoon for communism, it will be like all people staying together like this. So it's just a single whole lot of things where people live together. There is only one sect. Right? Now let's see the performance of the reactor. So I hope you understood how this works. Right? Now let's see the performance of the reactors. Performance. I will draw these once again. Now I have these two. Now let's say a reaction like A giving B takes place. Just a simple isomerization kind of reaction takes place. In this case, what happens? The moment it enters inside this MFR, there will be some concentration, right? But that concentration will be throughout the reactor, because that's how we have assumed the mixed flow reactor to be. There will be some concentration, and that will be the concentration throughout the reactor. But in this case, at this point, Ca will be higher, and as it goes here, Ca will be lower. And as we all know, the expression for rate, assuming a power law kind of kinetics, that R is equal to K into Ca power n, where n is the order of the reaction, all those things you might be knowing. So higher the Ca, higher the rate of the reaction. So if you compare these two in a MFR, there is a averaged out Ca, right? Ca is normalized, so the value of Ca will not be high or low, it will be say somewhere in the middle. So the rate will be averaged out. But in case of PFR, at initial point rate will be very high. At this point rate will be high and this point rate will be low. So ultimately it happens, it turns out mathematically. Also you can prove that, which I will perhaps do it later. But at this point, for a positive order reaction, for a positive order reaction, PFR gives higher conversions. Why does this happen? Because the rate is very high in PFR initially and very low in PFR towards the end, whereas in MFR there is only one rate which will be averaged out. So due to the higher rate, the conversion will be higher. Right? So what does this imply? Does this imply that PFR is always better? Because most reactions are positive order reactions. Does this imply that PFR is always better? Does this imply, in other words, that capitalism is always better? Not at all. These are just outcomes of a situation. For example, speed is not everything you need in life, right? It's not like a road is empty, I can travel faster and I'll reach the destination faster, so I have to take that road. It depends on where you have to go. For example, if you have a reaction like this, we all know what selectivity is. For example, say you have a reaction like A giving B and A giving C and maybe something like this, and say this is your only desired product, all other things are undesired. If you simply put A in a PFR just because the reaction is faster, you will end up getting D and D, which are absolutely not required. Right? What you need is C, which is required. So one reason for having a choice of reactors, whether you should go with a MFR or a PFR, depends on your selectivity. Conversion, selectivity, two important points. There is one third very crucial and very beautiful thing which it should be the last thing I will be talking about today, is something related to fluid mechanics. Now, what is the I should be perhaps asking like this. Now, this is a laminar flow. We all know it's parabolic in nature. You have derived the equation, Poisson equation, all those things. So it's parabolic in nature. What happens in this is laminar, right? This is laminar. What happens in the flow is turbulent. The profile is kind of flattened out, and it's more of parabola here. It's parabola. I put this inside brackets. It's a parabola. So this will be flattened in case of a turbulent flow. It gets flattened. The front part, this region gets flatter. Imagine increasing the velocity. Imagine increasing the velocity. I mean, it's just imagination. We are still in the fantasy world. We are still increasing the velocity to a limit until it reaches something like this. It's the flattest possible configuration, and this is what we call as plug flow. So remember, plug flow is somewhere is a point where the velocity is very high. So this should be in this case the Reynolds number is around 10 power 6 for a cylindrical pipe. Imagine where this will be. This will be an unattainable velocity. That's why plug flow is ideal, of course, but the velocity is very high even if you need to get somewhere close to the plug flow. That's why what happens sometimes, now if a reaction needs, say, residence time, you all know it, the amount of time the reactant has to be inside a reactor for a certain conversion. We would have calculated that. Say if residence time has to be 10 minutes. This is what you calculated, and you need to design a reactor where the residence time could be 10 minutes. If you are in a situation to maintain a plug flow with this much high velocity, you would probably need kilometers of reactor. No, you would probably need kilometers of reactor to attain 10 minutes, which means the reactant has to stay inside the reactor for 10 minutes when it is flowing at such a high velocity. So with that velocity, if it has to stay inside the reactor for 10 minutes, then what it means is basically you need a very long reactor. And we have one more restriction. Which is for a plug flow, this pipe, the L by D ratio, we can't go after a limit. You can't use a tube like so large to maintain a plug flow, because the wall effects are very crucial, right? The wall effects matter. So you can't maintain a plug flow where the L by D ratio exceeds the limit. So you have, but when you take a mixed flow reactor, say if your residence time is 10 minutes or your volume is some meter cube, you can change L as much as you want. Similarly, you can change the diameter as much as you want. You have a control over the geometry of the reactor. You have control over the geometry of the reactor in case of a mixed flow reactor, whereas you don't have the control over the geometry of the reactor when it's come to the plug flow reactor. Similarly, one more issue is the residence time. If it's very high, then it's impossible to construct a plug flow reactor. It should be kilometers of length, right? So these are the reasons why MFR exists. Even so, I'll put them together. Reasons why MFR exists, even if being slow. So one is sorry about this pen. Selectivity. The second is maintaining a plug flow is a challenge in most cases. Maintaining plug flow is a challenge in most cases. As we told, you have to maintain a plug flow, which means the velocity has to be very high, and so which means the L by D cannot be varied more than a limit. And the last thing is residence time, right? So these are the three reasons why we still have an MFR. We have to compare which one will work, which one will need less metal, which will be easier to construct, easier to maintain, easier to operate, all those things. And we have to choose a reactor which is closer. Ultimately, you can't build an ideal PFR, you can't build an ideal MFR, but you can, it's like two extremes, and you can choose one which is closer to whichever is feasible to you. I hope the analogy was good enough to understand, right? And very soon we will talk another interesting topic from chemical engineering. I have a few topics. If you have any, please put down in the comment section. We will take up and discuss that as well, right? Thank you so much for listening. Please do subscribe, share this video. Thank you.